Alrighty, welcome back to 353. Thank you for joining me today. So, today we start our journey talking about threads, the actual hardest topic of the course. So, let's just dive into it. So, first we have to talk about, I said at the beginning of the course, there's like concurrency and parallelism usually mean the same thing in English, like they're synonyms. Not so in computing, so this is our first aside that concurrency and parallelism aren't the same if we're talking about computing. So concurrency is just switching between two or more things. Like you can get interrupted, you can get preempted, you can make progress on one thing for a bit, switch back to another, and make progress on something else. Goal with concurrency is just to make progress on multiple things. You can have concurrency with just a single CPU core, just switching back and forth really fast. Parallelism is actually running two or more things at the same time instant, and to do that, they would have to be independent, and the goal there is just to run as fast as possible. Now, as a note here, if you are not that fast, you can make concurrency kind of look like parallelism. So think if you were just like at some table, someone was drinking, had like a glass of red drink in front of them and a blue drink. If you closed your eyes for 10 seconds and then they were halfway done both of them, well, you don't know what they did. They could have, just downed both of them at the same time, or they could have just switched back and forth. You don't even know how many times. So depending on the period you're actually looking at this and observing it, well, concurrency may look like parallelism even though it's not the same. That's how back in the day, we can make the illusion that we have parallelism even though we only have like a single CPU core. All right, so real life analogy to just get the idea of concurrency and parallelism. You can assume that you're sitting at a table for dinner and you have four options you can do. You can eat, drink, talk, and gesture with your hands, and we're assuming we're slightly polite people, but there's this weird caveat that you're so hungry that like if you start eating, you won't stop until you finish. So through this, we can argue about for any two tasks, can I do those two tasks in parallel? Can I do them concurrently? Can I do one, not the other? Or maybe the other way around. So like, let's say drinking and talking, those two tasks, and we're assuming we're not savages. So for eating and drinking, I can't do them in parallel, right? Because I'm just using my mouth. I can either talk or drink. I can switch back and forth between them, so I can do them concurrently, but I can't do them in parallel. Again, polite dinner things. So those are tasks I can do so I can't switch back and forth between them. So I can't do them concurrently and I can't do them in parallel. What about gesturing and talking? Well, I can do that right now. I can do them in parallel. I can do them concurrently if I want. I can switch back and forth between them. I could stop doing one if I wanted to, or I could just do them both at the same time. And then gesturing and eating, well, I can do those things in parallel, but I can't do them concurrently because of that stupid caveat where if I'm so hungry, I can't stop until I'm done. So that gives all the situations. So any questions about that, just to try and relate that to a more real life situation. So concurrency, parallelism, not the same. So there's just so you have it, just in case. But now we get to dive into threads. So threads are like processes with shared memory, which makes things very, very difficult for you. So same principle as processes, except by default, they share memory. So they have their own registers, like including the program counter and stack. Those are the only thing that are independent with threads. Otherwise, they share memory within that process. So they have the same address space as the process. So any change you make appears in all threads, which makes things complicated, but it also makes things fast. So if you want to have memory specific to a thread, you have to explicitly state it. That's something called thread local storage, or TLS. So there is a way to get memory specific to a thread, or you can just malloc, get memory yourself, and then make sure only one thread accesses it. So there's some options if you do want some independence. So the relationship between processes and threads is one process can have multiple threads within it. So by default, like a process just executes code in its own address space, or in other words, its own virtual memory. Threads actually just allow multiple executions in that same address space, so they all have the same virtual memory. They're lighter weight, less expensive to create than processes, and they're going to share code, file descriptors, and everything like that. So when we created a process, it had to have its own address space. We now know a bit more from working on Lab 3 that it would have to get, its own page tables, everything like that. It'd also have to get, new process would also have to get a new copy of all the open files and what they point to, and then on top of, the virtual registers and everything like that. So threads, they just need a stack, new set of virtual registers, and that's it. Everything else is in the process's address space, so it uses the same page tables, same open files, everything like that. So, like I said, even assuming we have a single CPU core, threads let us express concurrency. So even if you have a super, super low power device, they might be worthwhile. So a process, it can appear like it's multiple, executing in multiple locations at once. However, the operating system is just context switching within a process really, really quickly. And that is accomplished through threads. So it might be easier to program concurrently and not have to deal with, in case something blocks, then you can make progress on something else. So for instance, what web servers typically look like is they'll just have a while true, and then they'll just sit here and block on a request from the user, wait for someone to connect to it. And then once someone connects, this will return, it will unblock, and then they'll create a thread to process a request. So it could do, hundreds of requests concurrently, maybe in parallel, but at least concurrently. And then it could immediately just go back into this with the main thread and wait for the next request and be able to, react to it as soon as it comes in, make progress on it, and go back and forth. So we'll see how to do network IPC in the next lecture, but this is the basis for every web server. They kind of all look like this. So threads, lighter weight than processes. So for a process, completely independent address space, so independent code, data, and heap between processes, but between threads in the same processes, they all share code, data, and heap because, well, they live within a process. Processes, completely independent execution, and threads live within a process, so they must live within an executing process. If we don't have a process, we don't have any threads running. So they'll both have its own stack and registers. You might find it easier to think about just a process by default has a single thread in it, and a thread is what is doing the actual execution. Then for processes, right, it's expensive to create them and context switching because, well, mostly to do with virtual memory, so it would have to create copies of all the page tables. And then now we know when you context switch, it would have to flush the TLB and all that stuff, which is fairly expensive, especially because, well, you want to keep your caches as valid as possible. But threads, they're fairly cheap to create, just a stack, some registers, that's it. Easy to context switch to, don't have to, if you're within the same process, you don't have to change address spaces or anything like that. TLB is still valid, all of that fun stuff. So when a process exits and someone waits on it, it's completely removed, everything to do with it, all of its memory, all of its open files, everything like that. While if a thread ends, the only thing that's removed from it is the resources it consumed, which is just a stack, and maybe some virtual registers and some other bookkeeping information. And when a process dies or terminates, all the threads within it die as well. So in this course, we'll be using POSIX threads. So for Windows, there's like a Win32 thread, but we're going to use Unix threads. So this is available on Mac OS, Linux, FreeBSD, all those fun things. So all you have to do to use it, include a pthread.h, and then when you compile and link, you just do -pthread, and that will go ahead, find the include directories, and then do the linking with the library. And all the pthread functions have documentation in the man pages, but they're going to work a bit different than our C wrappers for system calls. So unlike fork, where we just, after fork returns, two things are kind of active at the same time. Two processes are active and you don't know which is going to execute. With threads, it's a bit more clear-cut because you kind of direct a thread. So you create threads with pthread create, probably a more obvious name than just fork. So what it takes is just a pointer to a pthread struct, whatever that type is, and it will go ahead and initialize that for you, which is why it's a pointer argument. There's some attributes you can set if you want, and then there's a start routine. So it's C, so it's kind of hard to read what that means. So if you don't know what that means, that is a pointer to a function called start routine that takes a void star input. So it just takes a pointer input and then returns a void star or a pointer. So it takes a pointer as input and returns a pointer. And then the final argument in pthread create is just a pointer argument, and that will be passed to that start routine function whenever that thread starts executing. So the function, so after pthread create successfully returns, you will have another thread, and you don't know if you're going to continue executing on the main thread or the new thread is going to execute. But whenever the new thread executes, it starts execution at this start routine. So it starts executing that function. And then we can, of course, just give it a value to pass to that function here. All the pthread create functions, they return 0 if they're successful, not -1, unlike the C wrappers. And otherwise, they just directly return an error number if something bad has happened. And if something bad happens of this, the contents of the thread are undefined. So here is what that looks like. So let's go to this. So here I just, declare a thread, a pthread type. I'll call it thread, and then I do pthread create. So I give it the address of the thread. I'll do null attributes, so I'll just take all the defaults. I'll tell it I want to start running this function called run, and here's this run function. So it takes a pointer, which I don't use, so I said I don't use it, so the compiler leaves me alone, and then I return a pointer, and eventually I just return null. So the value of the argument I give it is just null because I don't care about it, and then after I have pthread create, I have the main thread, which might do printf in main, or if the operating system or kernel decides to schedule the other thread, it would just print in run, and I would see that printed, and then when it returns null, it's done. So yeah, if this was a process as review, am I missing anything? So for processes, we created with fork, and then what's the question we always ask ourselves once we create a new process? Yeah? Not quite. Something we need to do. Yeah? Check the exit status after it dies, or like more high level, you need to be a non-neglectful parent, right? So in this case, well, everything's living within a process, and it's like, oh, okay, well, I don't know when the other thread is actually done executing, so maybe there's an equivalent here for waiting on a thread, or waiting on a process, but the thread version of it. Because if I try and run this, something interesting will happen. It'll just print in main. not printing in run even though there's another thread that could actually run. If I execute it a few times, let's see how lucky I get. Oh, hell yeah. All right, so this weird thing's happening again. So I saw in run twice. I forget, so that happens because there's like some parallelism problem with printf, so that's real fun. Yeah, I can explain that, but it's actually two printf calls, and it's something to do with the buffer being weird and not flushing properly. So if I don't get stupid, unlucky, let's see, if I run it a bunch of times, all right, didn't get unlucky, but I also wasn't a good parent to it. I didn't wait on it or anything like that. So there is a wait equivalent for threads, and they call it join. Why do they call it join? I don't know. Why can't they be consistent and you like wait on a process or wait on a thread? Again, don't ask me. So the wait equivalent for threads called join. So it's pthread join. You tell it what thread you want to wait on, and then you get a pointer to a pointer, and that's the return value. So it will just update that value with a pointer value, which is what the function returns. So that's basically how you get its exit status. Because with processes, right, main returned an int. So we did like a pointer to an int to get the value back out of it once we did wait. So same thing for threads, except that they return a pointer. So in order to get the value set, we need a pointer to a pointer because, yeah, that's just how C works. So same thing, return 0 on success, error number otherwise, and we should only call this one time a thread. So if you call it multiple times on the same thread, that doesn't give you an error like with the wait system call. C just says it's undefined behavior and you are now on your own. So if I wanted to see both lines print, all I have to do is say pthread join, tell it the thread, and I don't care about the return. So now if I run this, I'll see in main, in run every single time. Because now the main thread, after it prints in main, if it gets scheduled first, it will join on the thread I created, so it will wait for it to finish until before it actually returns 0, which just exits the process. So again, if I did not have this join, what was happening before was the main thread came, created a new thread, and it was going to execute this in run if it got scheduled. But the main thread kept running, it printed in main, and then it hit return 0. And once it hit return 0, that's the same as calling exit, which ends the process. And because it ended the process, all the threads within the process are also gone. So the thread that was about to print in run just never got to run before the process died. But now when I have a join, if the main thread goes ahead and executes first, it'll wait for the other one to finish before it hits return 0 and then exits the process. So again, we'll see both things printed every time. So questions about that? Yeah?
So like, what exactly does the pthread underscore t object represent? Is that just like an address of the thread?
Yeah, so this pthread underscore t object basically is just like record keeping for the thread. So it's kind of like a process control block, but for a thread. So you can think of it as like a thread control block. So like it would have the address of the stack that that thread uses and like a place to store all of its virtual registers and things like that. If it was implemented in some ways, maybe that's in the kernel, maybe it's just keeping track of the stack.
But like when we're interacting with it, we could just sort of treat it as like representing that thread.
Yeah.
Like nothing more to that.
Yeah, just represents the thread. You don't really have to worry about it. It's implementation details. You don't have to concern yourself because it'll change depending on what kind of thread it is, which we'll get into later. And you'll also implement this in lab 4. So the thread lab is probably more fun than the virtual memory one, but you'll get to learn about this. But there's helper functions, so you don't have to deal with registers and all that fun stuff. All right. Any other questions? Yeah?
Why does it always print in main before being run?
So yeah, question is, why does it always print in main before in run? That just has to do with the scheduler because, well, creating a thread is fast and it's very, very likely that, we talked about the completely fair scheduler, how it kind of gets like a time slice. So it's very likely that the main thread just still has time remaining, and it's very likely that it'll just continue executing until the process is done. But if I change the scheduler, this might not be true anymore, right? All right, any other questions before we break it even more? All right, so main thing here is just, remember, we just return 0. This is the same as exit from a process, and then everything, all the threads get removed. All right, so here's the code. So all we did was we added a join, which is like a wait, make sure we're good parents, even though there's no parent-child relationship for threads because they all live within a process. So if you wanted to, you can join on any thread you want. Even if you don't create it, you still just have to follow the rules where you can only join on a thread once. Otherwise, you have undefined behavior. And similarly to waiting on a process, when you join a thread, after join returns, all the thread's resources are cleaned up, so like its stack and everything like that. So there's also an equivalent for threads for, like we did exit and that terminated a process. Well, there's a way to terminate a thread. So if I want to end a thread early, the kind of corresponding call to exit is called, thankfully, in this case, pthread exit. So in the case of threads, their functions just return a pointer. So before we just had exit that had an int. Now we have pthread exit that has a pointer. So the return value is just the value passed, like that's passed to the function that calls pthread join. And start routine is kind of like the equivalent of just main. So it all has all the same rules. So if you return from that start routine, that will automatically call pthread exit for you, just like returning from main automatically calls exit for you. So they kind of have like a one-to-one relation. So just think of the difference between main and pthread, or main and exit. That's the same as whatever start routine you give it and pthread exit. So like I said, implicitly called at the end of start routine whenever the thread returns. So unlike processes, we are allowed to just kind of ignore being a responsible parent. In this case, with, again, no parent-child relationship. So there is a thing called detached threads. So joinable threads, which are the default thing, will wait until someone calls pthread join to clean up all the resources because, you need to get the return value. You may actually want to check, what their output is or something like that. So if you don't care about its return value at all, you don't want to read it anyways, there is an option to just detach a thread. So a detached thread will just release their resources immediately when they terminate. Whenever they call exit, their resources get cleaned up immediately. You can't call join on them because they're not joinable threads. So the drawback is you can't get a return value out of them, but also you don't have to remember to join them to clean up all the resources because there is also an equivalent of, just like we have zombie processes, we can have zombie threads. If we have a joinable thread and we don't join, same concept, it'll just like waste some resources. But if we have a detached thread, it cannot be a zombie thread because as soon as it exits, it gets cleaned up. And also for threads, there's no concept of an orphan thread because they live within a process. If the process is dead, they don't get reparented or anything like that. They live within a process. If the process is dead, they're dead. So for pthread detach, it's just a function, pthread detach, and you give it a thread, and it will mark the thread as detached. And it says if you call pthread detached on a thread that's already detached, it's undefined behavior because, of course it is, it's C, so why would they make your life easy? So here, I can just do that same example. So here is the same thing. So I will just create a thread that executes this run function. Again, I don't care about the argument, and I don't care about the return value. And then I'll detach it, and then just do the print in main and print in run. And if I go ahead and run that, whoops, it's called detached error. I get the same thing as I had before, right? I just got in main because, well, so happened that the main thread created a new thread. It was able to execute this in-run function, but the scheduler just decided to keep going and then return 0, and the process is now dead. And so the other thread is dead. So if I run this a whole bunch of times, likely it's just going to be in main. Oh, I got lucky once, and I got in main in run. But again, we don't have to do that. But now, if I wanted to always have both of them print, before my solution was to just we put a join here and waited for the other thread to terminate before I stopped. But now I can't. So I can't join on the thread now because it's detached. So the question might be, how do I actually wait and I don't exit my process until every single thread is done? Yeah?
Can you just wait? Create a sleep?
If you create a sleep to solve concurrency issues, that is a Band-Aid and may or may not work. So the problem here is basically this, right? This returns 0 in the main thread, that exits the process, terminates the process, and then everything goes away. So turns out that the thing that is calling main, you think of it as the main thread because it's a thread like any other thread. So there are rules where if you have multiple threads going and they all call pthread exit, well, your process will actually stay alive until the last thread calls pthread exit, and the last thread will go ahead and call exit for you. So if instead I wanted to make sure all of my threads are done before my program is done, I can just do a pthread exit here. And this pthread exit, well, when this executes, my main thread is now done. So my main thread now has terminated, and it wouldn't continue to get to this line. It would be impossible to get to that line now because now the main thread has terminated. It now no longer exists. And then since there's only one thread eligible to run now in this process, well, my scheduler is going to have to pick this at some point, and then it's going to do printf in main, and then it's going to return null, which actually does the implicit pthread exit. And then the library is going to go, oh, okay, well, this is the last thread in the process, so I should just terminate the process now because there's nothing else to run. So if I go ahead and, whoops, if I run this now, I should see every single time I see in main, in run, I see them both. I don't know what order they're going to be in. Very likely in main is going to come first because of the scheduler, but again, I can't guarantee it. And come on, flip, whoops. All right, we're not gonna get lucky today. All right, whatever, yeah.
What could you do if you needed one thread to run before another one?
Yeah, so the question, what can I do if I want one thread to definitely run before the other one? And we will need till after reading week to get into that, but we will learn how to do that. So that's called synchronization. So yeah, you might want to orchestrate things between threads, but after reading week. Yeah. Valid to return something on the stack of a thread? What do you mean?
Like for the return value.
Yep.
Is it valid to return the address as a local variable for the return value? Because the stack doesn't get free until we join.
So but whenever you exit from, like return from the function, it gets freed, so you shouldn't do it. So yeah, the question was, if I do like some local variable, let's say int x equals something, and I just did like this, right? So for the same reason, you don't want to do just that if you have, you know, so like, yeah, is that foo a good idea? So no, because, well, this local variable only exists as long as the function exists. Wherever you hit return, doesn't exist anymore. So you're pointing at memory that could be freed. It's undefined behavior. We'll have an example of this later too, but the compiler also just yells at me. So it says, function returns the address of a local variable. Shouldn't do that for lots of reasons. But yeah, we should not do that. So if you want to like return the pointer to something, you'd probably have to malloc it or something like that. So I could malloc something, get a pointer back, and return that. And then on join, they get the pointer, they can use it all they want, and then they can free it when they're done. Is usually how it goes. All right, any other questions? All right, so here is our solution. Like I said, all we did was we put the pthread exit here at main, so that the main thread, we just exited the main thread, it terminated the main thread, and prevented the main thread from actually terminating the whole process. So now the code kind of works more as we expect. So you can use these attributes too if you want to like get set thread variables. So for instance, it's kind of ugly to use, but I mean, it's C, so it is what it is. So if you wanted to actually use the attributes, we don't have to use them in this course, so we'll either just use the defaults or at most we'll detach something. But if you wanted to use them, you just create an attributes. You have to initialize them with this init, and then there's a whole bunch of attributes. One of them would be like the stack size. So we can just get the stack size to just see whatever the default is, and print off whatever the default is, destroy this. So running this on most systems, it will show you that the stack size is 8 megabytes, and one of the other attributes is this joinable. So you could just set a thread to be joinable, which is the default, or you could create a thread that is detached, so that is also an attribute you can set. So like you could set detached state pthread detached, so you don't have to do a separate detach call, but setting that attribute is so common, they just made a pthread detach function for you, so you don't have to deal with this attribute thing. All right, so, all right, so we can compare like creating threads to processes and show that, you know, they're technically faster. So I didn't show that before. So here, I have a bunch of like, I have some other programs here we can play with. So there's one that creates 50,000 forks, so it creates 50,000 processes. And then this one, it creates 50,000 threads. So we can just see how expensive they are. So I can time, create fork. I don't have time, okay, cool. So if I time that and wait, see, it's like 6 seconds real time, 6.4. Well, if I just do the pthreads, oops. What is wrong with my keyboard? If I do the same thing with pthreads, hey, seems to be a lot faster. But, you know, they share memory by default. Other examples we can go into, so multiple thread examples. So here we have a loop here, so we have I going from 1 all the way to 4. We create a new thread. So I wrote this new thread function that will just create a thread for us, takes an ID, and then checks if there's any error. And then here in the main, before we return from main, we do a pthread exit, so we get rid of the main thread. So in new thread, this is where I show you like how we pass an argument to it. So I can't just, give it a pointer to this ID because it only exists as long as this function exists. You don't know when the thread will actually execute. So in order to give it an integer, the right way to do it is, okay, well, I have to malloc some space for it. So I malloc 4 bytes for the space of an int. I get back an int pointer. I write the value to whatever that pointer is pointing to. Then I create a thread, and here I set its attribute to none. I tell it to execute the run function whenever we give that function, and then I give it the argument, which would just be the pointer that malloc returned. And then in the run, okay, well, I know based off what I pass to this function that arg, so again, void star is like C's way of saying it's a pointer. It's up to you to figure out what the hell it's pointing to. So I know that arg is a pointer to an int, so I can cast it to a pointer to an int, and then dereference it to get its value. So now I have its ID now in a local variable, which is, again, since threads have their own stacks, this will be local to the thread, so nothing else can interfere with it. So now it gets the ID in this local variable called ID, and then, well, we should free things. So I don't need that malloc space anymore. It has done its duty, so I can just free it. And then here I have a for loop that goes 0 all the way to 9, and it'll just print off like thread ID and then sleep for a little bit. So now if I execute this, I'll see, I won't really know the order between the threads. In fact, it seems to switch every single iteration. So I have thread 3, 1, 2, and 4, all printing off 0, and then I have thread 1, 3, 4, 2, printing off 1, then 1, 3, 4, 2 again, then 1, 4, 3, 2. And again, don't know the order between them, but they'll all march on like this. So, questions about that? All right, well, just to prove that weird things will happen, let's say malloc. Yeah, that's hard. Screw malloc. So don't need you, and let's just say, let's just give you the address of ID, right? And then let's say I don't need you. All right, what's going to happen if I do something like this? A brave soul. Here, let's stare at it for a minute and think about what in the blue hell is going to happen with this. Yeah.
Is it eventually gonna, like, when it becomes something else that it cleans up, it's eventually gonna start printing out garbage because the ID is no longer defined?
So each thread is going to print different garbage or the same garbage?
I'd assume that each one receives a pointer to a different thing, but what it's storing eventually becomes garbage.
So each one will have its own unique garbage?
Yes.
All right, we got unique garbage for each one. Any other guesses? Oh, wait, are you amending?
Garbage for each one after some point.
After some point, okay. So maybe okay for a little bit and then all hell break loose? Okay. Yeah.
Maybe it's a seg fault because the liquids don't share their stack.
Seg fault because so the threads aren't supposed to share their own stack, but again, everything's in the same address space, right? So they could, maybe. So what's your vote? Things are just going to be random? Or yeah, someone save, help. Random, going to be good, all random, or we going to agree? All right, well, let's execute and see. So this will not be good. Whoops. Oh, I opened a new shell. Whoops. Oh, it's still running. No, it's not. All right. Wait, did that actually, I did not save. There we go. So I got thread 3440, 3440, 4430, 443. So I got some random stuff. Yeah, yeah.
So is this because essentially when a thread, executes, it sort of cleared up its memory, and then the next thread when you created it was like, oh, this address space is now, available, and then it wrote its thread ID into where the other one used to be? Is that why we end up with like duplicates of 0443?
Yeah, so this one, 0443, so that's
since you replace the other one?
yeah, that's a good idea. So let's see if we can get any patterns. So if we run it again, we got 0023.
Could we print out the addresses of each of these?
Oh, so you want to print off their addresses
Yeah, but the pointer.
in run?
So you can just,
Red got arg, something like that. Ooh, oh, we screwed it up. Oh no, we've introduced a new bug. So they all got the actual same address. Why is that? So don't we do like we do 4 different function calls to this, right? Well, turns out the main thread is the only one that does function calls to it, so it'll get some stack space, and then, yeah, so it'll get some stack space for this argument, and then create the thread, and then return, and then do another function call, and well, it's going to call the same function, so it's going to get the same amount of stack space, and the pointers are always going to line up. They're always going to be the same pointer in this case. So all the functions just get some random, all get the same address, which is supposed to be like local to this new thread function. And then since they all get the same pointer in here, the way they use it is they just read whatever value that they get whenever they start executing. So that's why we got some that were the same number, because it just so happened that before the main thread can change that value, so it changed that value by another function call, the other thread just read that value, and whatever value it read is what it set ID to. So, main could go ahead, create 2 threads, and maybe that value is 0, and then main doesn't run anymore, and then while one thread runs, reads the value 0, the other thread runs, reads the value 0, and now they're both duplicates. And after that, it's not going to change because I only read that pointer value once. If I wanted to make this like real bad, I could just say, instead of just reading it into this variable, let's just say I, just dereference it every single time. So every time I do a print, I'm going to just read that value. So now in this case, if I run this, okay, if I get rid of the printf because it's messing with the stack, oh, now it's just doing that whole value all the time. Cool. All right, so moral of the story is don't do this. So I want to make sure that my memory is actually independent, and because, well, in here, if I create a local variable in new thread, and the main thread is the only thing that calls it, that local variable only exists for that thread. I should not share it between threads, otherwise real bad things would happen. And this is kind of the source of bugs that last for like 7 years in the kernel because they're really hard to figure out. Yeah?
Why are we now getting, 65535 as the ID for all of them instead of, 1 of 0, 1, 2, or 3?
So now we're just getting it because likely we just got unlucky and this thread exited and just some crap happened to its memory. So
Oh, I guess, yeah, because it's no longer assigned, right? We're not keeping track of it.
yeah, so in this case we just always get that value now, which,
So something might be overriding that memory.
yeah, so I mean, so that this thread finishes, it cleans up the memory, and I read it every time, and it probably gets all cleaned up whenever this hits pthread exit. Before I had this, so it might be the case where that value is still valid because the main thread hasn't called exit yet, and the other ones just read that, and it still happens to be valid, and yeah, that seems to be the case. So, seems that pthread exit will go ahead and just kind of delete the stack and just set its value to just some weird numbers, because I'm pretty sure if I just like put a sleep here and then waited for a second until I read the value, I'm probably going to see the weird big value every single time. So, but moral of the story is you don't want to do that. So this is why they taught you how to use malloc and free and all that stuff. So now I have to, you know, actually argue about it between threads. Yeah.
So when we're talking initially about threads, we were talking about concurrency and running things in parallel.
Yeah.
Different processes can run both concurrently as well as in parallel because they're completely independent from each other. But can multiple threads run in parallel as well, or can multiple cores run different threads of the same process?
Yeah, so your operating system, so the question is like, okay, can threads run in parallel or not? And that is up to the kernel. So threads will always be concurrent, so it can switch between them. But the goal of the operating system is to run things as fast as possible too. So if I have, 8 cores on my machine, I want 8 threads to all run at the same time, and I want it to run in parallel. So the kernel will hopefully run all these things in parallel. You have to argue about their safety, you can argue just about concurrency. So you just want parallelism for it to go fast. Yeah.
So similar to how wait had a no-hang wait when we were looking at it for different processes, is there essentially a no-hang version of the exit, the wait for the exit thread?
Yeah, so the question is, for pthread join, does it have a no-hang version? And the answer to that is no. It does not.
So
Yeah.
is there no way to check essentially the status of a thread without it exiting?
Yeah, there's
Well, I guess they share memory, but
yeah, so they share memory, so it's up to you to figure that out. So they just said, they share memory, so you don't have to do IPC, right? Everything's nice and free because everything's on the same address space. Just read, hopefully, the correct memory value so that it actually works. All right, any other quick questions before we wrap up? So just to wrap up, whoops. So threads, they enable at least concurrency, hopefully parallelism. So we related them to something we already know, processes. Right now, they're just lighter weight. They share memory by default, and each process can have multiple threads, but just one to start. So way to think about it is a process by default will just have a single thread that runs main. We call it the main thread. Otherwise, we can create more threads after that. They all live within a process. So just remember, phone for you. We're all in this together.